Let's now have a look at the class of binaries which are known as spectroscopic binaries. If you have gone through the videos on visual binaries, astrometric binaries, you saw that you are measuring the position as a function of time. If you have gone through the video of spectrum binaries, then you'll realize that we are measuring the light or photon as a function of its wavelength. Now, when it comes to spectroscopic binaries, you are measuring the light as a function of its wavelength as well as time. Okay? So, here you have to understand that the spectrum is a function of time. Okay? How does it happen? All of you know Doppler shift, right? You have a wave, and depending on the relative velocities of the source and the observer, the wavelength changes. Okay? Now, light is also a wave, electromagnetic wave. So, the wavelength of the light as measured by the observer will change when there is a relative velocity between them, as long as both are not stationary, right? So now a binary star that is having a motion is continuously changing its velocity component with respect to the observer, and hence the wavelength will continuously change as measured by the observer. So now what you need to have is very good spectral resolution so that small changes in wavelength can be measured. At the same time, very good timing resolution. Of course, the timing resolution is important when you are making observation over a small scale of time. If your system is changing over decades, then you need not have very good timing resolution, but you need to have good spectral resolution. But if we are talking about ultra compact binaries, where the binary periodicity is of the order of tens of minutes or hours, then you have to have a very good timing resolution. So, this is your formula for Doppler shift, that delta lambda, which is the change in the lambda from the value of lambda which you measure when both are stationary. So, that particular value is lambda naught, which is in the denominator. At any given point of time, you are measuring lambda, and the difference is lambda minus lambda naught, which is delta lambda. The ratio of the two is given by v upon c, where c is the speed of light and v is the velocity of the source. Here we are actually assuming the observer to be stationary. Okay, we are not talking about the velocity of the observer. If you want to take that velocity into account, it will come in the denominator. And as we all know that the velocity of rotation of the earth is very small compared to the velocity of light. So that particular correction can be ignored, and in the denominator we write only c, whereas v is the velocity at the given instant of the source that is moving. So now this particular line is the value, this value and this value is the value of the lambda when the source is stationary. So that happens when it is moving along this direction or this direction, because here you do not have any velocity along the direction of line of sight. So then what happens? These lambda correspond to the actual lambda of the source when it is assumed to be stationary. When it is here moving, it is moving towards the observer, it will be blue shifted. So this line appears towards the blue. And when it is here, it will be red shifted, this appears here. Okay? And then again blue shifted, it will appear here. So this shift of the lines gives you the velocity. Now understand, you are measuring the velocity of an cosmic object millions of kilometers away from you. Just from our understanding of atomic physics and Doppler physics. This is just a small animation, how the lines move when the lines due to the two objects are moving. Okay. If it happens, you can measure the spectrum separate of the two objects also. You see two set of lines moving out of phase with each other. Or it might happen that you see only one spectrum where the line is moving. You are unable to get the flux from the second star.